idea that matter is composed of small, indivisible particles was first put forward by the ancient Greeks. Science owes an enormous amount to J.J. Thomson, who isolated the electron and realized it was part of an atom, and to Ernest Rutherford, under whose direction the experiment firing alpha particles through gold leaf brought us to the realization that an atom consisted of a tiny, positively charged nucleus, surrounded by a great deal of space in which there were negatively charged electrons. Diagrams such as these are frequently shown in textbooks. We're pretty certain that they are not accurate. They are, however, easy to draw and able to convey basic ideas. The blue dots in these diagrams represent the electrons. Following Rutherford's work, researchers identified two major particles in the nucleus. These are the proton and the neutron. Together, these in the nucleus account for almost all of the mass of the atom. Electrons have a mass of only 1/2000th of that of a proton or a neutron. The mass is very close to zero, and they have a negative charge. Measured in atomic mass units, protons and neutrons have a mass of 1. Neutrons have no charge, but protons have a charge of 1+. The overall charge on an atom in equilibrium is 0. The number of protons is exactly matched by a number of electrons. It is the number of protons that defines an element. This is a representation of a helium atom, that is the second element in the periodic table. The element symbol He is written with two numbers, one above and one below. As part of this explanation, we'll split the atom into its component parts. The protons are represented by the red dots, the black dots are neutrons, and the blue are electrons. On the symbol, the number 2 represents the proton number, the number of protons in the nucleus. It's sometimes called the atomic number. In an atom such as this, which is electrically neutral, the number of electrons will be the same as the number of protons. The number above the symbol is the nucleon number. It is the total of the number of protons plus the number of neutrons. We'll look at this information with a couple more examples. The oxygen atom shown here has 8 protons in its nucleus and therefore must have 8 electrons. The nucleon number is 16. Since 8 of those are protons, the other 8 must be neutrons. The final example is argon. It has 18 protons in its nucleus and therefore again 18 electrons. The nucleon number is 40. We know that there are 18 protons and therefore there must be 40 minus 18, that is 22 neutrons. Larger atoms have always got more neutrons than protons. Almost all elements exist in more than one form. These different forms are called isotopes. Pictured here is the most common isotope of carbon, that is carbon-12. If we split this picture into its component parts, we can see that the atom has 6 protons, 6 neutrons, and 6 electrons. There are, however, other isotopes of carbon, for example carbon-14, which contains 2 more neutrons than carbon-12. These extra neutrons have no effect on its chemical properties or its identity as carbon. The atoms with extra neutrons will be slightly heavier and may be atomically unstable. By that I mean they may be radioactive. For a last example, let's take the most common element in the universe, hydrogen. The most abundant isotope is hydrogen with 1 proton and 1 electron. There are, however, 2 other isotopes, one with an additional neutron and a third with 2 additional neutrons. Isotopes of an element, therefore, have exactly the same number of protons and exactly the same chemical properties, but they have a different number of neutrons. Thank you for watching.
The British scientist Ernest Rutherford was one of the first to show that radioactivity could consist of 3 distinct types of radiation. The 3 types differ in their response to an electric field. A source of radioactivity is passed through a hole to form a beam. The beam is directed at a fluorescent screen, which is illuminated when it is struck. In the absence of an electric field, all the radioactivity beam strikes the target at a single point. When an electric field is applied, the initial beam is separated into three components. One of these is deflected upward by the electric field, indicating that it is negatively charged. These radioactive emissions are called beta rays. A part of the beam is deflected downward, indicating that these particles are positively charged. These radioactive emissions are called alpha rays. Notice that the alpha particles are deflected less than the beta particles by the same electric field. This occurs because the alpha particles are more massive, but the amount of deflection is also determined by the relative energies of the different types of radiation. The portion of the original beam that is undeflected is due to radiation that is not charged. These emissions are referred to as gamma rays. Other experiments showed later that the beta rays are actually high-speed electrons. The alpha particles proved to be helium nuclei. The gamma rays are high-energy photons, analogous to X-rays.